A very good morning to all of you. If you have knowledge, let others light their candles in it. Margaret Fuller. We warmly welcome our esteemed guest speaker, Professor Sibnath Kayal, a professor in materials engineering of Jindal University, India, and our academic staff and students from University of Peradeniya to the 10th session of isoTalks organized by the Society of Chemical and Process Engineering students. I'm Tanuja Bandara from A16 batch of Chemical and Process Engineering, and I will be your moderator for today's session. Let me start with a brief introduction to isoTalks. isoTalks is the newly launched initiative by the Society of Chemical and Process Engineering students, mainly focusing on mitigating the gap between their current academic curriculum and the substantial world of industry and higher education. This program consists of 3 elements. The first element is a talk series, which is a series of webinars with the industry and academic professionals. This is accompanied by a discussion series, which is a series of casual talks on the most interesting aspects of chemical and process engineering. And the final element is a series of workshops programmed to brush up skills in working with simulation software. 9 previous isoTalks were conducted under different, intriguing, and timely themes with the help of industrial and academic professionals from all around the world. And for anyone interested, we have entered the link of previous sessions in the chat box. Today, we are going to commence the 10th chapter of the talk series, isoTalk 10, to address the theme, Smart Hybrid Porous Materials for Sustainable Development of Low Carbon Future. And for that, now I invite Dr. Nadesh Adhisurya from the Department of Chemical and Process Engineering to introduce our renowned guest speaker, Professor Sibnath Kayal.
Right. Thank you, Tanuja, and a pleasant morning all. First of all, thank you very much, Professor Kayal, for accepting our invitation to deliver an interesting talk today. So as Tanuja mentioned, my job will be to introduce today's speaker, Professor Sibnath Kayal. He completed his B.Tech in Chemical Technology from University of Calcutta in 2002, followed by an M.Tech in Material Science and Engineering from IIT Kanpur in 2011. Sorry, 2004. Sorry for the mistake. From his master's, he was able to secure a prestigious Silver Medal Award for the best M.Tech student in order of merit from IIT Kanpur. Then he obtained his PhD in Material Science and Engineering from Nanyang Technological University, TU, Singapore in 2012. After his PhD, he served as a Senior Product Development Engineer at Advanced Micro Devices Private Limited, Singapore for 2 years. Then he worked as a postdoctoral research fellow in NTU for 2 years. Currently, he is working as a professor in the Department of Metallurgical Engineering, Jindal University, India. His research focus is advanced materials, nanocomposites, synthesis and characterization of, and property evaluation of biomedical materials, sustainable clean energy technologies, etc. He has published numerous peer-reviewed journals and presented his finding in international conferences to date. With this note, I cordially invite Professor Sibnath Kayal to deliver his talk on smart hybrid porous materials for sustainable development of low carbon future. The floor is yours, Professor Kayal. Please proceed. Thank you very much.
Thank you, Dr. Nadis, for your nice introduction. Am I audible to you?
Yes, yes, Professor Kayal, everything.
Hello?
Yeah.
Okay, so let me share the screen for the PPT slide is visible. Hello. Yeah, can you visualize my screen?
Yes, sir, we can see.
Okay. First of all, I would like to thank the organizing members for giving me this opportunity to present the topic on smart hybrid porous materials for sustainable development of low carbon future. It is my privilege and indeed an honor for me. In this regard, I must mention the name of Deputy Vice Chancellor, Professor Dr. Terence Madhujit, for hosting me in the University of Peradeniya as a guest faculty. Myself, Dr. Sibnath Kayal, currently working as a professor in the Department of Metallurgical Engineering at OP Jindal University, India. Regarding our university, OP Jindal University is one of the top university in the central India. We have basically three schools, School of Engineering, School of Science, School of Management, offering B.Tech, M.Tech, BBA, MBA courses. Founded by the Jindal Education and Welfare Society, OP Jindal University was set up to bring high quality education to its students based on a world-class curriculum, the latest teaching methodology, and committed faculty members. The multidisciplinary university aims to develop young professionals and future leaders who will not only power the growth and development in the state, but also make a mark globally. So with this, let me go to my today's presentation topic. So basically, I will first introduce what are the different sources of energy and what are the sources of greenhouse gas emission, and why we require the need for carbon dioxide capture, why it is essential. Then I'll discuss about some alternative fuel to mitigate that low carbon footprint. So natural gas can be one of that. And in that aspect, I'll extensively use the role of advanced porous materials, how we can use this advanced porous materials for low carbon footprint. So basically, I will discuss about my research work. I have extensively carried out for this advanced porous materials, which is known as metal organic framework materials. This is a smart hybrid materials, and whatever mostly I'll discuss about how we have done the synthesis method, different characterizations. Then I'll show some of, and finally I draw the conclusion. As you know, the primary source of energy is the sun. As from the beginning of human civilization, sun is the primary source of energy. We take almost all our energy from the sun. The sun sends the energy that trees absorb and store. For many years, the human civilization, we used firewood as our primary source of energy. From our ancient age, we used to use the firewoods for our energy demand. Then we discovered coal, and using this coal, we started industrial revolution. Then we discovered oil and natural gas. So, but whether it is coal, oil, and natural gas, it is all ancient fossilized solar energy that's stored for 100 millions of years. That means the primary main source of energy is the sun. Whatever the fossil fuels we are currently using, the main ideal source is the sun. Then, whenever we use this fossil fuel for our energy demand, so there are, knowingly or unknowingly, we are increasing the greenhouse gases and greenhouse effect. So basically, this family of greenhouse gases comprise of carbon dioxide, methane, nitrous oxide, then perfluorocarbons, hydrofluorocarbons, then sulfur, hexafluoride, ozone, bromine compounds. So these are the greenhouse gases. Now, the Earth has a natural temperature control system, certain atmospheric gases that are critical to this system. On an average, 1/3 of the solar radiation that the Earth is reflected back to the space. Now that Earth's surface becomes warm, and as a result, it emits infrared radiation. Now the greenhouse gases trap this infrared radiation, thus warming the atmosphere. The naturally occurring greenhouse gases create the natural greenhouse effect. However, in the last centuries, human activities like burning of fossil fuels and deforestation have caused a jump in concentration of greenhouse gases in the atmosphere, resulting extra trapped heat, and therefore it resulting higher global temperature, which is known as, I think commonly we have already known, is quite popular now, global warming. All of us in the current era, we are now dealing with this global warming. So this global warming is caused by the large amount of concentration in the greenhouse gases in the atmosphere. So basically, burning of fossil fuels releases the greenhouse gas, carbon dioxide, into the atmosphere, which is regarded as the one of the major adverse contributor to the global climate changes. Now, the level of carbon dioxide concentration in the atmosphere has been increasing at an alarming pace. Now, this has caused serious environmental concern of global warming, which has drawn unprecedented public attention to the issue of CO2 emission. The adverse effect of global warming and climate change are melting of ice sheets, which results sea level rise, heavy rainfall across the globe, causing flood, landslides, extreme drought in some places, decline in crop productivity, ecosystems are changing, unnatural frequent cyclones, hurricanes, rise in atmospheric temperature, sea and ocean water becomes more acidic than it was 50 years before, impacting hard to the marine life and ecosystem. So in order to mitigate this global warming, carbon capture and storage technology has been seen worldwide as one of the most promising mitigation options that capture carbon dioxide from an industrial power plant and store it in a geological reservoir. However, there are some significant shortcomings associated with these CCA options, which are invariably it is a high investment cost, and sometimes what happens that possibility of leakage from the geological storage due to moderate size earthquakes and long-term liability issues and problems also with public acceptance of offshore storage location. Therefore, a more carbon dioxide capture and utilization technology in which waste carbon dioxide gas is not only dumped, rather it is converted into commercially valuable products. So therefore, as a partial alternative to geological storage of carbon capture storage, carbon capture utilization would be a better approach in terms of low carbon emission for long-term future. This is slide shows that it will give you the idea about the carbon footprint. Basically, this carbon footprint is defined as the amount of greenhouse gas emitted, okay, when we burn 1 unit of any fuel. 1 unit means like 1 kg of fuel. So how much amount of carbon dioxide? So let's say petrol, when we burn 1 liter of petrol, it actually emits equivalent to 2.3 kg of CO2. Similarly, for gasoline, 2.3 kg, and for diesel, 2.7 kg. Now imagine whenever we drive a car, let's say a car consumes 7.5 liter of diesel per 100 kilometer. Then a drive of 300 kilometer distance consumes almost 22.5 liter of diesel, which leads 60.75 kg of CO2 for this. Actually, it leads this amount of carbon footprint. So you can imagine how much carbon dioxide or that actually when we burn the fossil fuels, how much it leads to this carbon footprint to the atmosphere. Now, in the quest of finding solution to low carbon footprint, natural gas can be used as an alternative fuel for vehicles. The depletion of global fossil fuel reserves and the escalating environmental concern due to harmful emissions of greenhouse gases have put clean energy research on the urgent agenda. Natural gas, mainly consisting of methane, has the potential to substitute petroleum as a fuel for vehicles. CH4 combustion results lower emission of CO, carbon monoxide, carbon dioxide, sulfur dioxide, sulfur trioxide, nitrogen dioxide compared to other fossil fuel. Methane is also considered as non-toxic, non-corrosive, and non-carcinogenic, and presents no threat to soil, surface water, or groundwater. And methane is also available abundantly worldwide. It is 50% less costly than gasoline or diesel. And methane also has higher heating value. So in order to use this natural gas as a fuel, so there are different ways to this natural gas storage. First is the compressed natural gas, which is known as CNG. Also another is known as liquefied natural gas. However, the use of LNG is limited to the boiling off and pressure buildup and ambient conditions, and the complications of handling a cryogenic fuel. In compressed natural gas, CNG, natural gas is stored at very high pressure, around 200 to 300 bar. The use of CNG is limited to expensive multi-stage compressors that consume energy and require heavy, bulky fuel tanks. Therefore, the challenge of natural gas storage are low volumetric density, because methane at normal pressure and temperature, it exists in a gas density. So we require gas compression, which of course high investing cost. As an alternative, an LNG, which is known as adsorbed natural gas system, can be designed using porous adsorbent materials to store natural gas at relatively low pressure, which would permit lightweight, comfortable fuel tanks that can be optimally integrated into the limited space. So in this adsorbed natural gas storage system, advanced very pivotal role or crucial role to store this natural gas. In this aspect, the hybrid materials, which is known as metal organic framework, is very popular nowadays. Basically, this metal organic framework materials is composed of organic ligands, which coordinated to metal-based nodes, forming a three-dimensional extended network structure. The feature of this metal organic framework materials are that they have very large surface area, they have high pore volume, and their property, that means the porous property, can be highly tunable. So I have extensively studied this metal organic framework materials, which I will show you in my coming slides. Okay, so now coming to how this MOF, this is the metal organic materials that can be synthesized. So basically, conventional method is the solvothermal method. That means you require some metal salt and you need some organic ligand. So they are taken in as some organic or inorganic solvent, and we use some autoclave reactors to make a very high pressure, and we just heat it. Then what happens that at heat, after heating and at high pressure, this organic ligand and metal salt, they conjugate each other and form the metal organic framework materials as a three-dimensional structure. Then we do some solvent exchange and washing, and finally we do the drying to collect the parent metal organic framework materials. So now I'll show some of the individual metal organic framework which I have synthesized in our chemical lab. So first one is the amyl 101 chromium. So basically for this we used chromium nitrate salt, and ligand is benzene dicarboxylic acid, and we use water as a solvent, and HCl hydrochloric acid we use a very 2 drop HCl we used for as a catalyst, and we heat it at 200 degrees centigrade in the autoclave reactor. And you can see this blue sort of green color, this metal organic framework materials we have got. And the characteristic features that we have synthesized using a green method. Green method means we have used only water as a solvent. We didn't use any organic solvent. And also earlier people used hydrofluoric acid as a catalyst, but we have already actually we didn't use hydrofluoric acid because it's very hydrofluoric acid is a very toxic chemicals, hazardous chemicals, and it's really difficult to handle this hydrofluoric acid. So we avoided this hydrofluoric acid. Also, we have prepared some composite that is amyl 101 chromium using the MAXOB. MAXOB, this is the activated carbon. It is also MAXOB itself is a commercial activated carbon materials we have used to make a composite material. So basically, we have prepared the same method, but we have used additionally the MAXOB this adsorbent materials in the precursor materials, and the rest procedure is the same. Next, we have synthesized another MOF material that is HKUST1. So for this, we used metal salt was copper nitrate, and we used ligand as benzene tricarboxylic acid, and we used ethyl alcohol and water as a solvent, and we heated this mixture in an autoclave at 110 degrees centigrade for 24 hours, and we have got this bluish color of this MOF. Then we have synthesized another MOF material that is called aluminum fumarate. So for that, we have used the aluminum sulfate as an inorganic solvent, and organic ligand was the fumaric acid, and we have used the sodium hydroxide water as a solvent, and then we heated at 90 degrees centigrade for 2 hours, and we have got the white color of this aluminum fumarate. Next, another MOF we have synthesized, that is MOF 74. So for this, we used nickel nitrate as a precursor material, and we use organic ligand, and then we heat it in a at the mixture of ethyl alcohol and water as a solvent and heated at 110 degrees centigrade for 24 hours. We also prepared zirconium fumarate. This is also another zirconium based MOF materials. For that, we use zirconium oxychloride as a precursor inorganic salt, and we use the fumaric acid. We used completely water as a solvent for this synthesis of this zirconium fumarate. Okay, so following this electron microscope, then we used nitrogen adsorption desorption for surface area measurement. That is called the BT surface area. Then we have used thermogravimetric analysis to check that how much temperature this materials can withstand. That is the thermal, to measure the thermal for the storage of methane or carbon dioxide. So for that we require the adsorption behavior of this material, and also we have used some FTIR analysis. So I'm sharing you some of my results. Okay, so basically the BT surface area, whatever the synthesized materials, the porous materials, we have found that for Mi101 chromium, we have got the surface area 2235 meters square per gram, and whenever it is doped with some alkali metals, there is some decrease in the surface area. And for the composite material, we have got some increase in area to 670 So you can, this is a scanning electron micrograph. You can see the particles, the morphology range, and mostly uniform particles we achieved for this MOF synthesis. So this analysis we have to identify that is present in the synthesis chromium. We have found that the corresponding standard peak of one chromium, their corresponding lattice, the corresponding planes, and interestingly, after doping, what we observe that there is no change, or there is no shift in the peak position in the XRD. In the MOFS structure, MIL101 chromium has a cubic structure. That cubic structure is not disturbed by the doping. On the top, this is the max of composite. So basically, this XRD shows the corresponding peaks of the composite materials. So the left portion, these all peaks correspond to MIL101 phase, and this peaks corresponds to the activated carbon, which is the graphite phase that is present in the maxole. Okay, so basically the TGA analysis we have done to study what is the thermal stability of the synthesized material. That means how much this material can withstand the temperature. That means what will be their application temperature this material can be used. So for that, we have done the thermogravimetric analysis. So if you see that here, until this 150 degrees, until 100 degrees centigrade, there is a weight loss. This weight loss corresponds to the desorption of water molecules inside the MOF structure. You know, the water molecule, whatever they are, because this is a porous material. So that means whatever the moisture that is present in the atmosphere, this material will automatically absorb this moisture from the atmosphere. So whenever we hit above 100 degrees centigrade, this moisture, it evaporates out and it actually escapes from the MOF porous structure. And that's why there is a weight loss. Okay. So this weight loss corresponds to the desorption of water molecules from the MOF structure. Then you can see from 100 to around, I say 350 degrees centigrade, this range, there is a slow reduction or slow weight loss. And this slow weight loss is due to the, whatever the polymer materials or any other gases that are present inside the MOF structure. And so degradation of, this is not the complete degradation, but the degradation of the polymer chains that it stirs. Okay. And after that, you can see there is, after 350, you can see there is a sudden weight loss. And this sudden weight loss is due to the complete degradation or complete collapse of the MOF structure. So after this temperature, the structure, the MOF structure completely collapses. And that means after that, this structure is no more your MOF. So that is called the degradation temperature. So above this degradation temperature, that means the materials will collapse. So before this temperature, that will be your, so that material can withstand up to this temperature. Now, interesting features you can see whenever we use dopant like lithium, sodium, potassium, this degradation temperature slightly shifts towards the left. Now, this figure shows the methane absorption characteristic features. So basically, how this material can, so this diagram shows, or this slide shows. So basically, we have measured the absorption characteristic at different temperatures, at different pressures. Okay, so let's focus on the first one. Let's say MIL101 chromium. You can see the absorption, the absorption characteristic that decreases with increasing temperature. This is with the pressure. As we increase the pressure, the absorption capacity also increases. Okay. And okay, whenever we dope with lithium ion, what happens? That's adsorption characteristic that decreases. Okay. Similarly, when you dope with sodium, that adsorption capacity is further decreases. And potassium, when you dope with potassium, this adsorption capacity is lowest. Okay. So from this study, we can conclude that the adsorption capacity of methane gas decreases with increase in dopant size. That means this lithium, sodium, potassium ions, these are considered as the alkali ions. So whenever you go from lithium to sodium to potassium, so their atomic size or ionic radii increases. And these atoms or ions occupy the interstitial sides of the MOF structure. So it hinders the overall occupation from the methane gas. Okay, so that's why the adsorption capacity decreases with increasing size of the alkali dopants. And this is for the carbon dioxide absorption behavior. The same features, how this methane absorption property that this material this amyl 101 what and with its alkali dopants, what is the adsorption characteristic features? So this figure shows the same features you can observe. Point number 1, the adsorption capacity decreases with increase in temperature. Point number 2, the adsorption capacity increases with increase in pressure. And number 3, point number 3, the adsorption capacity decreases with increase in alkali ion dopant. The same observation we have found, and it is quite obvious. And this is the comparative study at room temperature that for maximal composites, the composite materials, basically this adsorption capacity actually increases at the same condition. Now this FTIR analysis actually we have performed to actually investigate whether after this adsorption of methane, structural deformation of the MOF structure. So for that, what we did, we have done the FTIR analysis, that is called Fourier transform infrared spectroscopy, before methane and CO2 adsorption and after methane and CO2 adsorption. And we have seen that you can see all their corresponding, basically you can see this 3394. Okay, this peak and around this 1620, this peak is due to the adsorbed water molecules, stretching and vibration, bending vibration of adsorbed water molecules. And this 1402 is basically OCO, that due to from dicarboxylate. That is the we have used benzene dicarboxylic acid as an organic ligand, and this peak comes from there. And this 600 to 1600, all these peaks corresponds to benzene ring. You know, benzene ring, the benzene dicarboxylic acid, it has benzene ring. So basically 1508 is due to C double bond C vibration. Then deformation vibration of carbon hydrogen bond, CH bond at 1160, then 1015, then 880 and 750. Okay, so all these peaks you can see before and after, all the peaks remain intact. Okay, so from this observation we can conclude that the adsorption of methane and CO2 does not deform, okay, does not deform the MOF structure. Okay, so this is, that means its structure, the MOF structure is completely integrated. It doesn't get any transformation after methane and CO2 adsorption. Okay, so let me summarize this whole presentations. So basically, this amyl 101 chromium MOF was synthesized by a modified fluorine-free synthesis route, and which is characterized by XRD, ACM, TGA, FTIR measurements. And methane CO2 adsorption characteristic show that the adsorption capacity decreases with increasing size of dopants, and this original parent MOF structure does not transform after methane and CO2 adsorption. So these are the main conclusion I can draw from my today's presentation. Thank you all for your attention. So I would love to answer if you have any queries. Please feel free to ask me.
Thank you very much, sir, for the valuable and insightful address to our topic today, smart hybrid porous materials for sustainable development of low carbon future. That was vastly informative and thought-provoking for all of us. And I'm pretty sure our audience learned a lot from you. And now we are ready to move on to another interesting segment, the Q&A session. Dear audience, we are ready to give you the opportunity to raise your questions. You can use the raised hand option to indicate that you have a question or a comment. Or else, you can simply type your question in the chat box and I will narrate your question to Professor Kayal. I hope everything is clear and this is your opportunity to get your doubts clarified and enrich your knowledge.
Is there any question?
Anuja, till others get ready, can I ask a question?
Yes, sir. You can ask.
Right. Thank you, Dr. Kayal, for your interesting talk on MOF and its application. So one of the main concern, like while I was listening to the presentation, you showed us different types of MOFs you synthesize. So I was wondering whether are they novel MOFs or existing ones, or if it is novel, did you elucidate the structure? Did you do single crystal X-ray and resolve the structure? Got the crystallographic aspect. I'm asking about the crystallographic aspect.
Okay, so basically this MOFs materials, that is people are now extensively studying these materials. So we have this amyl 101 chromium, whatever I have shown you. This is actually already Ferre group. Actually, they initially started this synthesis of this Ferre group. But the novel thing is that the synthesis method we have adopted. The Ferre group used this hydrofluoric acid as an activator. But the problem is that a hydrofluoric acid is a very corrosive in nature. That means the common normal means it's a very highly reactive actually. So it's quite difficult to handle this. So what we did that we have used some modified method, fluorine film method. So and the crystallographic, all the structure that actually the Ferre group they have already done. So we have already matched after our modified synthesis route, and we have found that identical crystal structures. Okay, so we haven't made that completely new MOF materials. Rather, we have made the synthesis. The route is different. We have used is a much more greener synthesis route. So a Ferre group they use the organic solvent that is called. They use that. The organic solvent was carbon tetrachloride, okay, but we have used as a water as a solvent, okay.
Right.
So yeah, so these are the different synthesis route we have adopted, and you can go through. Already this is the published paper. I have already referred in my presentation slide. So yeah, the detailed route is already we have described there. What is the modified? Yeah. Right.
So that means in terms of crystallographic aspects, both sets are having similar structures, and you have modified the synthesis method.
Yeah. Yes. Right.
Thank you, Dr. Khan. Thanks.
Is there any questions? I see a lot of students there they are attending. So you can feel free.
I am Anushka here. Maybe until students get ready, I will ask a question from Professor Kayal. Now, Professor Kayal, thank you very much for the insightful presentation and a lot of new knowledge. Actually, I'm not working in that field, so this is a very basic question. Now, this in CCS, carbon capturing and storage. So is it like, has it been practiced in the world in industrial scale right now, or is it still in research stage?
CCS technology, madam, is already extensively used in many countries, especially in Canada, and then in Australia, and then some portion of the Europe is already extensively used. But the problem is that, madam, the thing is that in normal the CCS, this carbon capture storage. That means you first capture the carbon from the atmosphere and store underground. Okay, so this is the basic principle. But the thing is that what happens that there are some countries which is very much prone to earthquake. So basically this under the what happens during the earthquake, basically this during the earthquake, what happens, this whatever the geological storage under the myth, so that gets damaged. So that is the main shortcomings for this CCS technology. Otherwise, CCS technology is quite extensively used. Basically, it captures carbon from the atmosphere and then convert it.
Yeah, what is the capturing mechanism used currently? How do they capture?
Okay, so basically they capture carbon using the form of some chemicals, like they convert carbon dioxide and use some minerals to convert into carbonate form. And that carbonate they store as a minerals form underneath. So this is one aspect. And other aspects that they simply convert this carbon dioxide to some useful product. Useful product means that CO2 is the gas form, and this CO2 gas that can be converted into some valuable product like methyl alcohol. So that means they some methane they convert to some value-added products. So CO2 they reacts with hydrogen using some catalyst like photo catalyst like titanium dioxide, or they use some palladium platinum as a catalyst, and they convert into some product like methyl alcohol, which can be used. So without recycling back to atmosphere, they can be used some valuable products.
Okay, thank you very much, Professor Kayal. I think now students, you should ask at least a few questions.
Thank you, madam. And sir, there is a question in the chat box. It says, sir, are there any studies done to compare MOFs and zeolites?
Okay, so basically zeolites. Zeolites is also porous materials, but zeolites is called the naturally occurring porous materials. Zeolites are basically the aluminosilicates. Okay, and it is also naturally occurring. But the MOFs, whatever I have mentioned, that is called the synthetic materials. That means we can synthesize these materials according to our needs. That means according to our pore structure, we can tune its pore property. So that actually its property we can tune up according to our need. How much pore we can design this MOFs by based on what will be the organic ligand, what will be the inorganic salt. So we have this flexibility in MOF materials. So that's why if you see, there are a lot of MOF materials people are designing day by day, and they are synthesizing this. But the zeolite is the naturally occurring substance, so you don't have any flexibility of that, and it has some already this is the naturally occurring, it's already a long time back, it is available, but people have realized its structure, the zeolites, and from there on people have designed this MOF structure using the metal node as well as the organic ligand. So this, based on this flexibility of designing part, we can tune the property and we can vary the pore structure. We can vary the pore volume and also surface area we can tune. So this flexibility we have in the MOF structure.
Thank you, sir. If you have any more questions, you can ask now. There is another question in the chat box. Is this research feasible in terms of monetary facilities and cost?
Yes, basically, of course, this is the MOFs. Of course, this is in the in the research phase. If you see the production cost is, yes, this is one factor that the cost of these MOF materials. But if you see that there is one company, this commercial company MOF, it is in the Switzerland. So they are adapting a much more commercial products that in terms of the MOF materials. But initially, yes, it involves some cost. cost means the because as I have already mentioned that this is you have to prepare using some chemicals, and for our lab scale production it is not so costly, but whenever you think for your practical application, that means mass scale, the large scale production, rightly yes, it is you require some cost. So but people are still finding what will be some different as I mentioned that these materials I have used in a water-based solvent. So definitely your cost will be minimized. But for large scale production, sometimes you require its initial cost. Yes, it involves some initial cost.
Yeah, Tanuja?
Yes, madam.
Yeah, looks like there are no more questions.
So if there is no questions, so we can conclude the session.
Okay, sir.
There's one more, like what is the lifetime of these materials? Yeah.
Okay, as I told you, that's lifetime. It's not. This material is lifetime is not a problem, but the problem is the thermal stability. As I showed you my TG analysis. Yeah, so this material is a highly stable material. So it is not degradable material. It's quite stable material.
Okay, thank you. Yeah, Tanuja, shall we
Until and
wind up?
unless you hit the material above its degradation temperature.
Okay, right. Thanks.
Thank you very much, sir, for sharing your invaluable experience gathered in your exemplary journey so far. Your explanations for our questions were easily understandable and reassuring. We believe now our audience has an idea of the importance of smart hybrid porous materials in promoting the sustainable development of a future with low carbon. And now I would like to invite Dr. Anushka Ilangasinghe, Head of the Department of Chemical and Process Engineering, to propose the vote of thanks.
Okay, thank you very much, Tanuja. I'm sorry, I don't have a camera in my office computer. So yeah, let me, first of all, thank you very much for giving me the opportunity to thank Professor Sibnath Kayal, Professor in Materials Engineering from OP Jindal University, India. Thank you very much, Professor Kayal, for spending your valuable time with us, sharing the knowledge, your research, your findings with us, with our students. And it was a very valuable talk. And we have Dr. Nadish here at our department as a material specialist. So I believe that this collaboration, this connection will be taken forward, and some of our students are already working in similar areas, so like new material development and characterization. So I hope this collaboration we will be able to take forward. And I think we have all the facilities in Sri Lanka for characterization. The equipment that you have mentioned in your presentation, we have them here in our department and in our university. So I think we can take this collaboration forward, and we will keep in touch. And first of all, I would like to thank our DVC, Professor Terence Majid. He's the one actually who introduced you to us and introduced you to Dr. Nadish, and that is how this came this way. And also I thank Dr. Nadish, despite his very busy schedule now, we have to start all the exams for our undergraduates next week. So we are in a very tight schedule, and that is why the students are also not here physically. This is their study leave. Right, so despite they have to study for their exam starting from next Monday, so I'm really happy that many of them have joined online to hear this valuable talk. So I thank them as well. And also I thank all the staff members who have joined here online despite their busy schedule, and SCAPE especially for organizing the event very nicely. And thank you very much all the SCAPES members who actively participated in organizing this. Okay, thank you so much, Professor Kayal. I also apologize if there are like any, because this is a very like a short notice and a very swift arrangement. So if anything, like if you felt uncomfortable in any situation, thank you very much. I apologize on behalf of the department because it's a very quick arrangement. So when arranging logistics, if there were any mistakes, so we apologize for that. Right. Okay. Thank you very much.
Thank you, Professor Dr. Anushka, for giving me this opportunity. It's a very wonderful experience for me as I can interact with the students, professors in the department. Of course, it will. I have also a nice experience. Okay. Hope to see you to take carry forward from here.
Yeah. Yes. Yes. Please be in touch. Probably you can exchange email addresses with Dr. Nadish, and we can keep the collaboration. And yeah.
Sure.
Yeah, we would like to work with you in future as well. Yeah. Thank you very much. Thanks.
Okay. My pleasure.
Thank you very much, sir, and thank you, madam. And thus, we have come to the conclusion of this amazing session. Hope you all have a wonderful time with us. Thank you, everyone, for joining us today amidst your busy schedules. So, with the hope of meeting you again on another memorable day with an inspiring topic, it's time for us to wind up today's session. Have a great day ahead. Stay safe.